Our next talk is entitled From One Time to Two Around Reusable Multi-Signature Without Nested Forking by Lior Rotem, Gil Segev, and Elion Yogev. And Elion is giving the talk.
Okay, hi everyone. So this is a joint work with Lior Rotem and Gil Segev, and this is about multi-signatures, so let's just jump in. What is a multi-signature? So it's a special kind of signature where we have some subset S of the parties. They all want to jointly sign the same message M. So this is the subset, and they want to sign the message. Importantly, they're going to sample their own public key and verification key. Okay? And then they're going to interact, okay, in some interaction phase, and at the end of the phase, they're going to output some signature. This is a sigma star. So this should be a compressed signature, okay, representing all of them, okay? Of course, a naive scheme can just, concatenate all the signatures, and we want this to be succinct. The verifier of this scheme, okay, over there, she's going to get the aggregated verification key. So here we have a non-interactive version, so we just have a procedure that deterministically takes all the verification keys and compresses them to one small verification key. Okay, the verifier is going to get the set S, okay, the verification key and the signature sigma star. Okay. What is roughly speaking, what is the soundness that we want? We have this adversary. The adversary can see many signatures. So what is seeing many signatures in this context? It can ask for many MIs and many subsets SI and see many different signatures for different messages with different groups. And also, she can control some of the parties of the group, maybe even all of them but one. And at the end, she needs to forge a signature. Okay. Multi-sigs, so these multi-signatures, multi-sigs allow for a set of parties to join. It's a permissionless system. As he said, each party samples its own public key and verification key. And kind of in the last few years, we really saw a surge in demand for these things, due mainly to blockchain applications, and mainly due to the fact that the compression of the verification key, the aggregation, is non-interactive. So we have really multi-sig, which are drop-in replacements, where you don't even know that the compressed signature and the aggregated signature and verification keys are even from a different scheme. And for some applications, if you have a smart contract that is smart enough, you can design a whole new system for this. Okay. Good. So the question is, how do we prove security, okay, of specific multi-sig schemes? And in this talk, I'm going to focus on signatures that are based on discrete log and prime order groups. Okay, and we're also going to focus on the plain public key model, okay, so we don't have some global setup or something like that between the players. Okay, and in the existing schemes, what we see that there's a lot of security loss in the proofs. And this is mainly due to something called the forking lemma, or here even nested applications of the forking lemma. I'm going to elaborate on this in a second, but as a point, it's with the security that we get is actually insufficient for the popular groups that we use, like 256 groups. So what do we do in practice? What are the alternative solutions? We either have new assumptions that are strong and we don't have a lot of insurance in, or we focus our attention to specific classes of attacks. In particular, for example, generic attacks, algebraic attacks, and so on. Okay. So 1 minute about the forking lemma. This is kind of a standard technique where we need to rerun the adversary to extract more information. Okay? And when we do that, we lose in the success probability of the adversary because we have to run it many times. For example, a standard discrete log security would say that the success probability to solve discrete log is t squared over p, where t is the running time of the adversary and p is the size of the group. And after applying the forking lemma, for example, in the proof of the famous Schnorr signature, what we get is that success probability of our adversary is only t squared over p to the half. okay, or we lose a factor of 2 in the security parameter. And in existing two-round schemes of multi-signatures, what we see that they have at least 2 applications of the forking lemma, okay? And intuitively, one is to extract the malicious keys. As I said, the malicious keys of the adversary might depend on the honest keys of the honest parties. And the second one, to extract the signature. As a result, what we have is a success probability is t squared over p to the 1 to the 4th, 1 over 4, okay? And this is not going to be good enough for 256 groups, 256-bit groups. Okay. So at this point, we're kind of looking at the situation. We're saying, let's take a step back, and let's think of the foundations of the security of multi-signatures. Okay? And we ask, what is the basic security notions that we can get without losing this additional security loss? So we propose 2 weaker notions for multisigs. Okay? They allow us to get better security bounds. Okay? So we don't have this nested applications. These 2 weaker notions suffices for many, many applications. And hopefully they are a stepping stone towards getting full-fledged security of multi-signatures. Okay. So the first notion, this is the one-time signatures. Okay? It allows the adversary to obtain a single signature. Okay? So just one. Last talk we talked about, talked about NIST. So this was actually a big success story for NIST. If you know the Sphinx scheme, so what they did to get a post-quantum signature, they actually started with a one-time signature and then boosted this to a full-fledged security. And did it in a very practical way. Okay, and so we have 2 different notions of one time, and this is because here we have a multi-signature. So the first one is just one signature. The second one is one group, but many signatures. Okay? So what is the one-time multisig? It's the same setting of multisigs, except now the adversary, okay, here, has only one message M and one set M. One message M and one set S, okay? So the adversary can ask only once to see a signature. What is the single set security? So it's the same. So we have a single set S, but now many different messages MI under the same set. Okay. As for applications, if you know about this UTXOs, these are kind of one-time constructs. So these are transactions that are like one time. Okay, so you create them, you create a fresh key every time you create them, and then you use them only once. Okay, and the second application is actually for standard transactions using account abstraction. So here what you do, you're going to create a one-time signature, and then you're going to sign the message that you want and a new public key for the next signature. Okay? And you're going to create this chain of signatures, and you're going to anyway put this on the blockchain. So we're exploiting the fact that anyway we have a blockchain, and this way you can reuse the one-time signatures again and again. Okay. And also the single set notion applies for any n over n signing, okay, that you want. It's not one time. Okay, so let's talk about our results. Our first main result, we have a new one-time multi-sig scheme. Okay, it's based on a random oracle model and any ring homomorphic one-way function. Okay, this can be constructed from DDH and RSA and stuff like that. The key advantage of our scheme, the signing is non-interactive, so this is very cool. Verification key is 2 groups elements, okay, so it's very succinct. In general, it's a very practical scheme. The signature is only 1 group element, and we only apply the forking lemma once, meaning that we get a security bound t squared over p to the half, which is exactly the security of standard Schnorr. And you can also extend this to a t time multisig, meaning you can ask for T queries for some small number T. Okay. The second result, this is a less practical result, more of a proof of concept result. So we show that you can go from one-time multisigs, okay, with non-interactive signing, to a single set multi-signature, okay, where you can ask for many signatures for the same set, if you have an ISK. And the key properties are we have a two-round signing. Okay, the verification and signature sizes are not very concretely efficient, but they are independent of the number of signers. Okay, this transformation uses no extra forking lemma application, so we get roughly the same security bounds that we had before. And this is a kind of a proof of concept that there's no inherent loss, okay, going from one-time signatures to single set multisigs. Okay. Finally, the last result is kind of a structure versus hardness result. It's a lower bound. We show that there is no fully black box construction of a one-time multi-signature, okay, from any one-way function. And this is, in stark contrast to standard signatures, where of course we can construct them from one-way function. And this explains why we need a stronger version of a one-way function, namely a homomorphic one-way function. Okay, and the lower bound works for almost all schemes. There's some caveats that you can read down here. Okay, but all our constructions satisfy this. Okay, so in the last minute that I have, I'm just going to show the construction of the one-time signature. I'm not going to talk about completeness and soundness and stuff like that. But I want you to see the scheme. So we're going to assume that we have some one-way function f in the sky from A to B. What is the keygen? So the keygen is just, we have a one-way function that's sample random things and output, a one-way function of what we're sampling. So every party I is going to sample xi and ri, and it's going to compute f of xi and f of ri and just publish this output. Okay, so this is the public key. Good. Now I want to sign, okay? I have a one-way function, I want to sign, okay? What can I release? I can release pre-images, but I cannot release the two pre-images or not even one. I need to release kind of some pairwise independent of them, okay? And I can do that because I have the homomorphic properties. So I'm not going to directly sign M. I'm going to sign this M prime, which is a hash of M in the group. I have to do it because I want this signature to be specific for the group S that we're signing, okay? So it has to have the set S inside. And then I'm just going to output this random linear combination, this random thing M prime times xi plus ri. Okay, so this is what I'm going to publish. This is my signature. Okay, how can I aggregate? Okay, aggregate is very natural. Okay, have the homomorphic properties, so I just can take the product of all the xi's and all the ri's. However, I have this aggregation to be specific for the group. So I take the powers of these AIs. What is AI? AI is just, some random hash of the group. So of all the verification keys of the people in the group. Okay, and this makes it specific for the group. And then aggregating the signature is quite easy. I just take the sum of all the signatures that I get. Oh, but I have these powers of AI, so I need to have the right coefficient here. So this is aggregation, and then verification. If you open up everything, this is exactly what the constraints from all of this. So this is the one-time scheme. You can see like the efficiency of this and the succinctness of the signature and the verification key. So you can use it in different applications, and that's it.
Okay, we have time for one question while the next speaker sets up. Maybe two.
Hey, why do you call this ring homomorphic one-way function? This is just a group homomorphism, no? I mean, you're not passing M through your function f, right?
No, so it's not our definition of ring homomorphic. So the exact definition of security that you want and to what group, and if it's a group of a ring, yeah. So we need a ring. I don't remember exactly the reason why it's a ring.
But it's homomorphic as a group
Yeah.
homomorphism. Yeah. Okay, thanks.
It seems like it might be hard, but can you flip which part is fixed? Can you have the same message with a lot of different sets without losing security?
Yeah, that's a good question. And no, I don't know how to achieve that. That is a very good question. I do not know how to achieve it, and I also don't know how to go to many, like from single set to go to many. You're saying like maybe you can go from single set, same message, to many sets, single message, and then maybe to full-fledged,
Okay, thanks.